Hi, this is Alex from devstories.eu. AlphaFold, Protein Structure Prediction, Episode 20 of 21. Scaling an AI model from 128 GPUs to 2,000 GPUs is not just about buying more hardware, it requires completely redesigning how the system breathes. When you add that much compute, you uncover massive bottlenecks in how your host machines talk to your accelerators. Resolving those bottlenecks requires building a high-throughput pipeline, which is exactly how researchers recently dropped AlphaFold pre-training from 7 days down to 10 hours. The blueprint for this architecture comes from the ScaleFold paper. The authors identified a brutal scaling reality. As you distribute a model across thousands of GPUs, the math workload per individual GPU shrinks. The GPUs finish their calculations so fast that the CPU cannot issue new kernel instructions quickly enough to keep them busy. The CPU overhead becomes the dominant bottleneck. To fix this, you remove the CPU from the execution loop using CUDA graphs. A CUDA graph captures a sequence of CUDA operations and their memory allocations into a single static graph. Once captured, the GPU executes the entire graph directly without waiting for the CPU to dispatch each individual kernel. Here is the key insight. You cannot just apply standard CUDA graphs to AlphaFold. The AlphaFold architecture uses a recycling mechanism, feeding predictions back into the model dynamically. This creates a dynamic computation graph. If the operations change, a standard CUDA graph breaks and must be recaptured, which ruins the performance gain. The ScaleFold paper solves this by designing a CUDA graph cache. Instead of one rigid graph, the system captures and stores multiple graphs representing the different recycling scenarios. When the dynamic execution shifts, the system simply pulls the correct pre-compiled graph from the cache. The CPU is bypassed completely. Now, the second piece of this high-throughput architecture, once your training step time is highly optimized, a new bottleneck appears. In a standard pipeline, training nodes pause periodically to run validation metrics. According to the ScaleFold paper, as step times shrink, this evaluation phase can consume up to 43% of the total pipeline time. Your massive, expensive training cluster sits idle for nearly half the time just checking its own work. The solution is asynchronous evaluation. You completely decouple validation from the training loop. Training nodes never pause. They constantly calculate gradients, update weights, and stream model checkpoints to a separate, dedicated pool of evaluation nodes. In the ScaleFold implementation, out of roughly 2,000 GPUs, only 32 were dedicated to evaluation. The rest did nothing but train. However, moving evaluation to separate nodes introduces a race condition. The evaluation nodes must finish validating a checkpoint before the training nodes produce the next one. If evaluation falls behind, your pipeline stalls. To guarantee the evaluation nodes keep up, the system bypasses disk storage entirely. The entire evaluation dataset is cached directly into CPU DRAM on the validation nodes. By eliminating CPU dispatch overhead with cached CUDA graphs and offloading evaluation to memory-cached asynchronous nodes, the pipeline never stops moving. The hardware is finally saturated. When architecting at scale, your primary job is no longer optimizing the math. Your primary job is preventing the GPUs from waiting. That's it for today. Thanks for listening. Go build something cool.